Okay, so first off, there was a warm up in Schoology. It's asking you what should be included in our class contract. Do take time to complete that. And then what we did today was I gave the students some ice at their table, and I asked them to describe how the particles would be moving in the ice as the kinetic energy continues to be transformed from the table to the container of the ice. And some things we had to remember was one, that kinetic energy is referring to your moving energy. The other thing that threw students a little bit was the particles. Particles is just a broad term that I want to use to describe atoms or molecules. Okay. Um, Eventually, we ended up discussing that here I have my table, and that's represented by the black line. And I'm simply going to draw the particles as circles. Okay. Since the table's in a solid state, then all those circles are next to each one, kind of crowded in together. Well, then I have my ice that's on top. It's also a solid, even though it is melting. And the ice is colder, so I distinguish that with a blue by putting it in blue. The table's warm, the ice is cold. We have a transfer of energy going from the table to the ice. And we all discussed, well, what would happen eventually in time? Well, in time, eventually, that is going to get to what we call an equilibrium. It's going to get to room temperature with everything, and you will no longer feel a difference between the ice and the table. It's all going to be the same temperature. And so a few more terms we talked about at that point was that ice and that table represents a system, and our classroom represents the universe. And in the fall, in the spring, we're going to actually isolate our systems and see what's happening in our systems, and we're talk about what that special term for that means. But just right now, just learning, looking at the ice and seeing what's happening with it. So then the next question I asked the students was, if the particles are behaving in the way that you have described above, how will the temperature of the ice change as it melts? The second question that follows that, as they're thinking about this, was, well, how can you test your idea in order to confirm if your model is accurate? Most students are going to tell me that they're going to put a thermometer in there, and they'll take the temperature over time and see what happens to the ice over time. Perfect. Exactly what we're talking about. Just getting you to think about, well, what's happening? How could I test for that? And most students would say that your temperature, your ice is going to go up because it's trying to get to equilibrium. Great. So the next question, this was a little bit harder for most students. I asked you to take a piece of ice, and I just set it at negative 40 degrees Celsius. If you recall, 0 degrees Celsius is your freezing point for water. And let's spell that out. So that's your freezing point. And as most students saw, was as soon as it got on the table, it starts melting. So for this scenario, I tell the students, I'm going to give you a piece of ice, and it's coming out of a container that's negative 40 degrees Celsius. And we're going to take this ice and we're going to place it into a beaker. Okay. We're going to set this beaker on a hot plate that's already warmed up, and it's going to be held on a constant temperature, and I'm going to heat this over time. And the question becomes, well, what would that graph look like? So I've got my beaker, and I've got my ice in it, and I've got a temperature probe, and I've got a source of heat. Okay, there you go. If you had to graph over time the temperature of that ice cube as it goes from solid, liquid to gas, what would that look like? And usually kids are like, well, I don't know. Like, I never really thought about that. So then I go on. Here's the next question. It says to draw the particle molecules for the water. There's 4 parts here, but we're going to limit it to solid, liquid, and gas. And A represents a solid, B represents a liquid, and C represents a gas. And so if you recall your states of matter, your solid is a solid because your particles are packed in. And since I'm dealing with the same item, then my particles are all the same size. Okay. Well, then what makes a solid become, well, what makes a liquid a liquid? And if you look at your water bottle, you'll notice, okay, you can shake it, it flows. And so here they're more spread out. They're still attracted to each other. That's why they fill the container, but they're more spread out. So then what makes it a gas? Well, a gas has a lot less because the particles are so spread out. And then we went back over the concept that this is highly compressible. Whoops. These are highly compressible. Oops. Just kidding. I hope you're paying attention. Gases are highly compressible because they're spread out. And these are not. They're low compressible. Then we also looked at the fact that these take the shape of the container. And these have intermolecular forces keeping them together. Gases do too, but not to the same extent as solid and liquids. So then we just thought again about the kinetic energy. Again, the kinetic energy is increasing as I go from solid, liquid, and gas. That's what's causing it to change. I showed them a pretty picture of water, and then we went to this graph. And this graph is in the document Beginning Chemistry Papers, and this is a testable question. So we went in there and we filled in, this is what your graph would look like if you did time versus temperature. Right here, where I have B to C and D to E, this is what usually catches students because they don't anticipate that you're going to have a level line. And most students, yeah, it's going to go up, it's going to go up. Well, we have a level line here because at these moments, when it's going from solid to liquid, liquid to solid, and liquid to gas, gas to liquid, on these green lines here, your water is trying to decide what to do. So you have solid and liquid existing at the same time as they're trying to figure out, do we have enough energy to go to become a liquid, or do I have I lost enough energy to become a solid? And that's why it's leveled off like that. This is a great test question. Okay. The other thing that we looked at was also this chart here, which is also in that packet. And we plugged in all the words. And the two that usually give most students trouble is deposition and sublimation. These are 2 words that are new to you. These 2 words mean that basically my solid is going to skip the phase, become a gas, and then the gas skips a phase and becomes a solid. There is no liquid phase. You see this with dry ice. Dry ice sublimes, it goes from solid to gas. You see this with iodine. Iodine will also do that. And the other one that throws students off a little bit is right here from liquid to gas, vaporization and evaporization. This is with heat. So when you're cooking at home, you are vaporizing the solution. This is nature. Nature evaporates. Okay. Then I also showed them this graph, which is the same thing. The only difference is I threw in the plasma just to let you know there is a fourth state. It's a highly ionized state of matter. So we generally play down here with the gases, solid, liquids. I also showed them this one. This is one that we will be talking about briefly in the future. Um, you have right here, this is the triple point. This is where all three phases exist. A little bit different from what you're used to because here's your solid, here's your liquid, and here's your gas. So the triple point, we have all three states of matter. And you notice that this graph is temperature versus pressure, right? The other point that I want to point out here is here's your critical point. It just basically means it can't decide what it's going to do. So it's really not a gas. It's not a liquid. And there you also there's your phase change verbiage that we've seen too. And then here's that graph again, just another way of showing you the same thing we already did, just noting where the freezing and melting is, the phase changes, and so forth. So note there are technically 4 fundamental states of matter that we only play with really solid, liquid, and gas as far as high school chemistry goes. And the last thing is this chart here. This is a nice one because it has solid, liquid, and gas and plasma, and it shows you what the particle representations would be for each one. And that's just to give you a visual to help you see what's happening.